Question number 1. What happens if two light waves with the same amplitude interfere constructively? Same amplitude, interfere constructively. What happens if they interfere destructively? If two waves have the same amplitude and interfere constructively, so these waves will support each other, and amplitude of the resultant wave is going to be doubled. And if one of them is, say, that y, the other one is y. So when they come across each other and interfere, so resultant amplitude is going to be 2y, twice. And we know that energy of a wave proportional to square of the amplitude. So if amplitude increases, of course, energy of the wave will increase, and it's going to be, for a light, brighter light, and it becomes much brighter compared to the component waves. But if destructive interference, one of them is, say, that displacement in positive phi direction, the other one is displacement negative phi direction. So when they come across each other, they will cancel each other, so completely cancel each other. So amplitude is going to be 0 in this case, and then if amplitude is 0, which means energy will be 0. If energy is 0 for a light, it is dark point or dark spot appears. Question number 2. Interference in sound is recognized by difference in volume. So if amplitude is greater, of course, power is greater. Power of the sound determines the volume. How is the interference in light recognized? So it's about the brightness. Interference in light is recognized by brightness, as when they interfere, two waves, just like in the first question. So the resultant amplitude will be greater, and then power of the light is going to be greater, and then more powerful light will be brightest. So that's why we can understand that if there's an interference or light, if the light gets brighter. Question number 3. A double-slit interference experiment is performed with red light and then again with blue light. In what ways do the two interference patterns differ? So same system, same setup. We have two slits. In this two-slit separation between the sources, say that S1 and S2, there is a screen. On the screen, you are going to form interference pattern, and one of them you will do red light. You will use a red light. In the second one, you are going to use blue light. So, what is the difference between the interference pattern? So, according to the path length difference, d sine theta is equal to m times lambda, this theta indicates position of a fringe with respect to central line. If I check the sine theta equation, which is equal to m lambda over t, for both red light and blue light, we are using the same system. That's why these are going to be same separation between the slits. And if you are looking the position of first bright fringe, for example, m's are the same for both blue and red, you should check lambda. So if lambda is longer, so sine theta is going to be greater, which means theta is going to be larger. As wavelength increases, angular displacement and the position angle of the fringe will increase. It will get larger. For example, this is going to be m is equal to 1 for longer wavelength light, which is red. This is going to be m is equal to 1 for blue light. So because blue has a shorter wavelength, its position angle or angular displacement is going to be small. For red light, its position angle or angular displacement is going to be big. Question number 4. What data would you need to collect to correctly calculate the wavelength of a light in double-slit experiment? In fact, in the previous question number 3, we explained that if you want to calculate the wavelength, we have to know the separation between the slits first. D must be known. What is D? And of course, you have to know the position angle of the point, which fringe, for example, m is equal to 1, m is equal to which one is it? You should know it. M must be known. This position angle must be known. And D, and separation between this source must be known. Why? Because d sine theta is equal to m times lambda for constructive interference. If you want to calculate lambda, so you have to divide both sides by m. So lambda is going to be d sine theta over m. So d must be known, 1, theta must be known, 2, and order of the bright fringe must be known, 3. This 3 must be known to calculate the wavelength of the light. Question number 5. If a double-slit experiment were performed underwater, how would the observed interference pattern be affected? Consider how light changes in medium with a higher index of refraction. So the difference between air and the water, this title is studied in the 10th grade. As light passes from air to water, its speed decreases. Yani air and water. In air, light is faster. In water, light is slower. This is the rule. In the 10th grade, you learned that. But frequency of the light doesn't change as it moves from one medium to another. We studied this in chapter 3, section 3. Frequency same. If faster the light, in this case, according to the speed equation, v is equal to lambda times f. V is constant. Pardon, f is constant, sorry. Frequency of the light is constant as it is moving from one medium to another. F is constant. If v is greater, wavelength must be longer. Yani in air, when the light is in air, traveling in air, wavelength is going to be longer. But when this light enters to the water, a wavelength gets shorter because speed and wavelength are directly proportional as a wave or light passes from one medium to another. Then we will go in this basic. What happens to the interference pattern? Many questions about what happens to interference pattern. Questions about theta. How does this theta changes? So we know sine theta equation. The sine theta is equal to m times lambda. So if you want to check how theta is affected, you should simplify these. So then sine theta is going to be m lambda over d. So as light passes from air to water, lambda wavelength gets shorter. If wavelength gets shorter, any fringe, first, second, third, whatever, it will get closer because as lambda gets smaller, of course, the sine theta and lambda directly proportional. Sine theta gets smaller as theta gets smaller. Yani fringe gets closer to each other. Yani in the air, if separation between the two fringes like this, for example, say the central bright fringe, this is first bright fringe, m is equal to 1. This is say that in air, when the light enters, when this experiment is done underwater, so in this case, it's going to be like this. Yani m is going to be at a smaller angle closer to the central bright fringe. So that's why fringes will get closer and closer when this experiment is done under water. Question number 6. Because of their great distance from sky, stars are essentially point sources of light. When you look at up to sky, you will see that stars seems to be like points. One point, one star, another point, another star. If two stars were near each other in the sky, say that two stars are close to each other like this, would the light from them produce interference pattern? Yani say that you put a screen on the earth or the surface, light traveling from one star, light traveling from the other star. Will they, when they meet, will they interfere? Will you observe interference pattern? Interference pattern can be observed if the waves or light from two sources is monochromatic plus coherent. Yani light from the two sources not monochromatic and also not coherent. And that's why you cannot observe an interference pattern on the screen which you put on the surface of the Earth. Question number 7. Assume that white light is provided by a single source in double-slit experiment. And there's a white light source in double-slit experiment. So here is the double-slit, one slit in here, other slit in here, S1 and S2. Describe the interference pattern if one slit is covered with red filter, the other one is covered with blue filter. So when we put here is a red filter in here, say that here is we put red filter, in here we put blue filter. Of course, red filter will let only red color to pass. Blue filter will allow blue color to pass. Different colors. We know that different colors of light do not interfere. They don't interfere, and you cannot see and observe. You cannot observe an interference pattern on the screen in this case. So to observe the interference pattern, the lights from the sources must be same single wavelength and same color. Blue or red. Red and blue cannot interfere. Question number 8. An interference pattern is formed by using green light and an apparatus in which the two slits can move away. And we have such a setup in the experiment setup. So there is one slit, another slit. Let me draw in here, in place. This is one slit. Here is separation between the slits S1 and S2. You are going to form interference pattern on a screen. So interference pattern is formed by using green light, and both S1 and S2 produce green light, and apparatus in which the two slits can move. And you can change the separation between the slits. Yeah, slits can move. That means that you can change D. If the slits are moved farther apart, and if D increases, moved farther apart means D increases. Will the separation of the bright fringes in the pattern decreases, increase or remains unchanged? This is when the separation between the bright fringes is questions about theta. How does theta changes? As theta, yeah, angular displacement or position angle of this bright fringe increases, then separation between fringe increases. So we will check that. Sin theta equation, we know that it's equal to m times lambda over d. Then if slits are moved farther apart, d increases according to the given question. If d increases, sin theta decreases. What does it mean? Theta decreases. Yani these, as theta decreases, the fringes will get closer to each other. Then separation between the bright fringe will decrease. Question number 9. Light falls on two slits spaced 0.33 meter apart. And separation between the slits T is 0.33 meter. If the angle between the first dark fringe and the central maximum is 0.055, this is theta. What is the wavelength of the light? So it's a first dark fringe. For first dark fringe, we are going to say that m is equal to 0. Yani in this equation, d sin theta m plus 0.5 lambda in the equation. And according to this equation, it's possible to write this equation in a different form, but in the 12th grade book, this equation is written that way. If the dark fringe is the first order, m is going to be one small number, 0. If the dark fringe is second order, m is equal to 1. If the dark fringe is third order, m is equal to 2. Fourth order, m is equal to 3. So m is going to be always 1 less than the order of the dark fringe. So because in here the first order, so m is going to be 1 less than first, yani 1 minus 1, it's going to be 0. M is equal to 0. We are going to write for m 0. D sin theta is equal to m plus 0.5, which is 1 over 2. I wrote 0.5. To calculate lambda, of course, you should divide both sides by m plus 0.5, m plus 0.5. So the lambda is going to be d sin theta over m plus 0.5. After that, you are going to insert them. 0.33 millimeter, which must be converted to meter. Millimeter to meter, we will multiply 10 to the power negative 3. Angle theta is given as 0.055. degrees, and m is 0 plus 0.5, and you continue with this calculator, you will get the result 6.33 times 10 to the negative 7 meter. But this is meter. We have general, they will give the choices in lambda, in nanometer. Nanometer, meter to nanometer, you have to multiply meter by 10 to the power of 9 to convert it to nanometer, as in here. So result is going to be 633 nanometer. A sodium vapor street lamp produces light that is nearly monochromatic, single color. If the light shines on a wooden door in which there are two straight parallel cracks, and just like slits, an interference pattern will form on a distant wall behind the door. The slits have the separation, D is given, separation between the slits is given, 0.3096 millimeter, and second order maximum. Maximum means bright fringe. Bright. Second order, m is equal to 2. M is equal to 2 and bright. Occurs at an angle, position angle of the fringe or angle of displacement sometimes, or because it's 0.218 degrees from the central maximum. Determine the following quantities: wavelength of the light. So this is the equation for constructive interference for bright fringe, d sine theta m lambda, because you will calculate lambda, divide by both sides m. So lambda is going to be d sine theta over m. This is given in the question in millimeter. It must be converted to meter by multiplying 10 to the power negative 3 meters. Angle is given in the question 0.218. M is equal to second order bright fringe 2. So result is going to be 5.89 times 10 to the power negative 7 meter. Again, mostly answers will be given in nanometers. That's why we should multiply meter by 10 to the power of 9 to get nanometer. Question number B, part B. The angle of the third order maximum. This time we know a lambda, we will get theta. And in part B, we'll get theta. Sine theta equation we are going to write. And d sine theta is equal to m lambda. To get sine theta, you should simplify d, divide by d. So then we will get m lambda over d. After that, we are going to insert the number. Third order maximum and bright, m is equal to 3. Lambda is calculated in first part, so we will use meter, not nanometer. That's why I will write directly in 5.89 times 10 to the power negative 7, divided by separation between these slits. It is given the question as 0.3096. It is millimeter, convert to meter by multiplying 10 to the power negative 3. You will get the angle. Angle between the fourth order maximum, the only difference we are going to write m is equal to 4 for C, so you can also repeat this question and you can get the angle. Question number 11. Why does light produce a pattern similar to an interference pattern when it passes through a single slit? This is about diffraction. Remember, according to Huygens principle, even though we see the slit to be very narrow, this slit compared to the light is very large, wavelength of the light very large, and Christian Huygens assumed that or considered that in this slit, even though we don't see, there are tiny light sources. These tiny light sources, of course, each one sends its own wave to the screen. So all these waves travel and then meets on the screen. According to the phase angle difference between them, if they are in phase, they constructively interfere. If they are out of phase by 180, destructively interfere. So we are going to see at different positions on the screen, some regions are bright, some regions are dark. Question number 12. How does the width of the central region of the single slit diffraction pattern change as the wavelength of the light changes? And if the question is about the pattern, it doesn't matter, double slit interference or single slit interference. Always we are going to check theta. If theta increases, pattern gets wider. Separation between the fringe increases. If theta gets smaller, pattern gets narrower and separation between the slits, between the fringe decreases. So, how does the width of the central region of a single pattern changes as wavelength of the light increases? And according to sine theta is equal to m lambda over d. If wavelength increases, sine theta proportionally increases. That's why theta increases. Yani if theta increases, the pattern gets wider and wider. The separation between the fringe, of course, will increase. So they will get farther. Question number 13. Why is the white light separated into a spectrum of colors when it is passed through the diffraction grating? White light composed of a spectrum of colors from red to violet. Red has a longer wavelength, violet has a shorter wavelength, shortest wavelength. Longest wavelength color, which is red, will have a greater theta. Yani position angle is going to be greatest, just like this. For red, this is going to be the angle theta. But for violet, it's going to be smaller theta. Then, because their positions are different, red has a different position than the blue, so you are going to see on the screen a spectrum of color from violet to red. For each bright fringe, you will observe that. For example, this is the first bright fringe. So from violet to red, m is equal to 2 from violet to red. M is equal to 3 again from violet to red. You are going to observe a spectrum of color from a color of the shorter wavelength to a color of longer wavelength. Then from violet to red. Question number 14. Monochromatic light shines through two different diffraction gratings. This time the gratings are different. The second grating produces a pattern in which the first order and second order maxima are more widely spread apart. Which means theta is big. Use this information to tell if there are more or fewer lines per centimeter in this second grating. In which first and second grating has a more widely theta. According to this, yani greater theta, greater angular separation. To make this greater, of course sine theta must be greater. To make sine theta greater, of course d must get smaller d. Why I go by d? Because slit spacing determined by the number of slits. Remember, equation was slit spacing was one or more number of lines. If slit spacing is going to be smaller, of course number of lines must be greater because they're inverse proportional. Yani a smaller slit spacing is due to the greater number of lines per centimeter. Then we can say that the second grating will have a greater number of lines in 1 per centimeter. Question number 15. If a light with a wavelength of 353 nanometer is passed through a diffraction grating with 795 slits per centimeter, find the angle at which one would observe second order maximum. Second order, m is equal to 2, which is maximum, and wavelength is given 353 nanometers. Calculate angle theta. We know that we are going to use the constructive interference equation because in bright fringes or maximas, all the constructive interference produces these bright fringes or maximas. We will calculate the angle. So divide by t, sine theta is m lambda over t, then theta is equal to sine inverse m lambda over t. So m is given, lambda is given, only we are going to convert lambda to meter. See, nanometer to meter, you should multiply by 10 to the power negative 9. Then we need slit spacing. Slit spacing, in 1 centimeter we have 795 slits. 1 centimeter divided by 795, but we will get result in centimeter. But a side unit distance length is not centimeter. That's why this 1 centimeter, it must be written in numerator in terms of meter, which is 0.01 meter divided by 795. So result is going to be 12.6 times 10 to the power negative 6 meter SI unit. After that, we will insert it instead of t. After that, you will use your calculator. Result is going to be 3.2. Question number 16. By attaching a diffraction grating spectroscope to an astronomical telescope, one can measure the spectral lines from a star and determine the star's chemical composition. And then this statement will be studied in chapter 8, how this happens, how we can determine the chemical composition of a star by using the light coming from the star. It's going to be studied in chapter 8. So the rest is for us important. Assume the grating has 3,661 slits per centimeter. This is a number of slits in 1 centimeter. We are going to use it for calculating the slit spacing, D. If the wavelengths of the star's light are 478.5 nanometers, 647.54 nanometer, and 696.4 nanometer, what are the angles at which the first order spectral line occurs? And first order spectral line means m is equal to 1. For each wavelength, lambda 1, lambda 2, and lambda 3, we are going to calculate angles, theta. So what is angle for lambda 1? What is angle for lambda 2? What is angle for lambda 3? And so on. We will find them. And B says at what angles these lines found in the second order. Yani you are going to repeat the part A for second order spectrum. Yani m is equal to 2. So let's do for the m, just m is equal to 1. And then for 2, you can do on your own a similar way. And I will now use the equation for diffraction grating, because in diffraction grating only constructed interference is observed, and then we determine the position of the bright fringes or maximas. D sine theta is equal to m times lambda, because I will calculate theta, so sine theta is going to be m lambda divided by D. Then I will inverse the equation. Theta is going to be sine inverse in bracket m lambda over D. So these angles now I will calculate theta 1 for lambda 1, theta 2 for lambda 2, theta 3 for lambda 3, one by one. So before that, I have to calculate what the D is. D is the slit spacing. According to question, in 1 centimeter there is 3,661 slits. So number of slits is lines 3,661. And 1 centimeter, of course, we should use a SI unit, not centimeter. 1 centimeter is equal to 0.01 meter. So when we divide them, we will get slit spacing, which is 2.73 times 10 to the power negative 6 meter. Then I am going to calculate what is the theta 1 for lambda 1. Just I will do lambda 1, yani for this way. What is the angle for this way? M is equal to 1. Because A asks just for the first order spectral line, m is equal to 1. Instead of m, I will write 1. Then wavelength of the first wavelength is 478.5 nanometer. Of course, we should convert it to meter by multiplying 10 to the power negative 9, divided by slit spacing, which is we just calculated in here. Then the result is going to be 10 degrees. Yani on this spectrometer, this light, whose wavelength is 478.5 nanometer, will appear at an angle of 10 degrees. And you can continue for lambda 2 and lambda 3. You can insert the wavelength in here, and you can find other wavelengths angles one by one. For second order, what you have to do, just the difference is instead of m is equal to 1, you are going to write m is equal to 2. For example, just 478.5 nanometer light I applied calculate theta 2, it is 20.5. Yani second bright fringe or second maximum appears at an angle of 20.5 degrees, and then repeat calculating theta 1 and theta 2 for other wavelengths 678.4 and 696.4 nanometer one by one. Question number 17. What properties does the laser light have that are not found in light used to light your home? In our home, we are using light which is more chromatic, yani it includes several colors, and also not coherent. Yani light in your house is not coherent, and also not monochromatic, yani chromatic. Several colors. But laser is not like this. Laser is coherent. It's coherent. And also, laser is monochromatic. And single color. So this is the difference between laser and the light we use in our home daily. Question number 18. Laser light is commonly used to demonstrate double-slit interference. Explain why laser lights are preferable to light from other sources for observing interference, because as explained in question number 17, laser light monochromatic and also coherent. So if we want to observe interference pattern, light sources must have monochromatic and coherent. That's why laser is used for double-slit interference experiments. Question number 19. Give two examples in which the uniform direction of the laser light is advantageous. Uniform direction of the laser light. Give two examples in which high intensity of laser light is advantageous. Uniform direction means it can travel very long distance. That's why you can use the laser for measuring long distances. And also they are used in compact distance lasers. Even it is written in somewhere, Earth's moon distance is measured by this way, by using the laser light. High intensity is about the power, more powerful laser. So you can use more powerful laser for cutting various materials. Question number 20. A 546.1 nanometer line in mercury is measured at an angle of 71 degrees. This is the wavelength of the speed of the light, and this light is measured at an angle of 81 degrees, which is theta, at the third order spectrum, yani third bright, third maximum, m is equal to 3 over diffraction grating. Calculate number of lines per centimeter. Of course, to calculate number of lines per centimeter, first you have to calculate what is the slit spacing. After slit spacing, we can get how many lines in per centimeter. So D must be calculated first. D sine theta is equal to m lambda. Then divide by sine theta both sides. Divide by sine theta. We will calculate D, m lambda over sine theta. M is third order. So m is equal to 3. Lambda is 546.1. Of course, we should convert it to meter by multiplying 10 to the power negative 9. Divided by sine of 81. Answer is 1.66 times 10 to the power negative 6 meter. Question is not asking number of lines per meter. That's why we should convert this slit spacing to centimeter because of this. So we can convert meter to centimeter by multiplying 10 to the power of positive 2. When we multiply this 1.66 times 10 to the power negative, it must be negative 4. I think there's a calculation mistake. Let me check it once. Yes, it must be 10 to the power negative 4 centimeter. This is the slit spacing. Then we know now slit spacing is equal to 1 over number of 1 centimeter divided by number of lines. Then cross product, when we cross product them, n is going to be 1 over d slit spacing in centimeter. So 1 divided by 1.66 times 10 to the power negative 4, answer is going to be 6,024 lines per centimeter. Question number 21. A double-slit interference experiment is performed using blue light from a hydrogen discharge tube. So blue light has a wavelength of 486 nanometer. The fifth order bright fringe, yani m is equal to 5, in the interference pattern is 0.578 degrees, yani theta, from the central maximum. How far apart two slits? And slit spacing is the question. Again, we will use this equation for constructive interference. This sine theta is equal to m lambda. Because this is calculated, divide both sides by sine theta. So this is going to be m lambda over sine theta. After that, you will insert numbers only. Convert nanometer to meter by multiplying 10 to the power negative 9. Divide by sine of 0.578. Result is going to be 2.41 times 10 to the power negative 4 meters. Question number 22. A beam containing light of wavelengths lambda 1 and lambda 2 pass through a set of parallel slits, and two lights, both of them passes through a double slit. In the interference pattern, on the screen they will observe interference pattern. Fourth bright line of lambda 1 and fourth bright fringe of lambda 1 occurs at the same position. Same position is the keyword. as the fifth bright fringe, and fifth bright fringe of the lambda 2. If lambda 1 is known as 540 nanometer, what is the value of the lambda 2? Two things are the same in here. One of them is because they are these lights, both of them, light 1 and light 2, they pass through the same diffraction grating, the same parallel slits. D is the same. Yani D is same for both lights. And also, they occur at the same position. Same position means their position angle theta also going to be the same. Yani D the same because this light passes through the same parallel slits. And also theta the same because they occur at the same position. Then for both lights, light 1 and light 2, for lambda 1 and lambda 2, left side same. Same for both lights. If the left side of the equation is the same, same for both wavelengths, right side of the equation also must be the same for both wavelengths. And m lambda is going to be same for both. Then I will write m lambda for both lights. For lambda 1, m1 times lambda 1. For light 2, m2 times lambda 2. Because lambda 1 is given, lambda 2 is the question, I am going to divide both sides by lambda m2, divide by m2, m2 will simplify. Lambda 2 is going to be m lambda 1 divided by m2. m1, fourth bright fringe, yani m1 is 4. Lambda 1 is given in the question as 540. m2, which is the fifth bright line, so m2 is going to be 5. I will write instead of m. And then I will get what is lambda 2. Lambda 2 is going to be 432 nanometers. 24. In an arrangement to demonstrate double-slit interference, lambda is given 643, angle is given 0.737, distance separation between the slits is given 0.50 millimeter. For light from the two slits interfere at this angle, what is the path difference both in millimeters and in terms of wavelengths? Will the interference correspond to maximum, a minimum, or intermediate condition? Okay, so path difference equation is clear. D sine theta is the path difference equation. So D is given in millimeters, theta is given. And because question is asking you find in millimeter first, just I will write D in millimeter, 0.15, as sine 0.737. So path difference is going to be, when this multiply them, it's going to be 1.93 times 10 to the power of 3 millimeter. This is answer in terms of millimeters. But it also asks you in terms of wavelengths. What does in terms of wavelengths means? Because we know that path length difference can be, for maximums or bright fringes, path length difference can be multiple number of the wavelengths. Yani, how many wavelengths, if the question path length difference, in fact it's asking you what is m. Find m. M is equal to then path length difference divided by lambda. A path length difference in millimeter, I know it. So I have to convert it into centimeter, into meter. A millimeter to meter, you should multiply once again 10 to the power negative 3. It's going to be 1.93 times 10 to the power negative 6 meter. Then what is wavelength in meter? 643 nanometer. So multiply by 10 to the power 9. So when we divide them, we will get m as 3. Yani it is going to be 3 lambda. Yani path length difference is going to be 3 lambda. 3 lambda, in 3 lambda path length difference, which interference occurs? Constructive or destructive? If the path length difference is the multiple number of lambda, 1 lambda, 2 lambda, 3 lambda, 4 lambda, and so on, constructive interference appears. But if the path length difference is 0.5, 1.5, 3.5, 2.5, 3.5 lambda, in this case, destructive interference occurs. Because it is integer, it's going to be constructive interference. Yeah, maximum. It's going to be a maximum condition for a maximum. And some standard test prep questions. Question number 1. In the equations for interference, what does the term represent? D is the slit spacing or separation between two slits. Yani B is the correct answer. Which of the following must be true for two waves with identical amplitudes and wavelengths to undergo complete destructive? To complete destructive, they must be in opposite direction, yani and also equal in amplitude. The wave must have 180 degrees out of the phase, which means they are opposite in directions of displacement, and also out of phase all the time. C is the correct answer. Which equation correctly describes the condition for observing the third dark fringe? For third dark fringe, and the order of the dark fringe is third, but m is going to be written 2. And equation for the dark fringe or destructive interference in light, the sine theta is going to be m plus 1 over 2 lambda. So third dark fringe, m is equal to 2, 2 plus 1 over 2 lambda, it's going to be 5 over 2 lambda. So this is C as the answer. Question number 4. Why is the diffraction of the sound easier to observe than diffraction of visible light? Longer wavelength waves diffracts more. Sound wavelength is very, very long compared to the light wavelength. Sound waves have longer wavelengths than visible light waves, so bend more around the barrier. B is the correct answer. Question number 5. Monochromatic infrared waves with a wavelength of 750 nanometer, which is lambda, pass through two narrow slits. If the slits are 25 centimeter apart, which is D, at what angle will the fourth order bright fringe appear? So m is equal to 4. Use the constructive interference equation. D sine theta is equal to m lambda. Then sine theta is going to be m lambda over d. Then theta is going to be inverse, sine inverse m lambda over d. M is 4. Lambda is 750 nanometer. Convert to meter by multiplying 10 to the power negative 9. The d is 25 centimeter. I think this is 25. The meter apart is so huge. It must be micrometer most probably. Later we multiply by 10 to the power negative 6. 25 micrometer apart, so 25 micrometers converted to meters by 10 to the power negative 6. Result is going to be 6.89. And question number 6. Monochromatic light with a wavelength of 604 nanometer pass through diffraction grating that has 5 times 10 to the power 4 light per meter. A bright line on the screen appears at an angle of 11.1 degrees, which is theta. What is the order of the bright line? We will find m. First, we should calculate slit spacing. Slit spacing is 1 over number of lines. 1 meter is given. It's clear, you don't need to convert it. 1 meter. In 1 meter, there are 4 times 10 to the power 4 lines. Slit spacing is going to be 2 times 10 to the power negative 5. After that, we will use d sine theta is equal to m lambda equation. Then m is going to be d sine theta divided by lambda. D is 2 times 10 to the power negative 5. We just calculated. Angle is given 11.1 sine 11.1. Wavelength is given 504 nanometer. Of course, we should convert it to meter by multiplying 10 to the power negative 9. Result is m is equal to 6. What is the property of a laser cold that causes coherent light to be emitted? Stimulated emission. Stimulated emission produces photons which are identical to each other. Both have, all the photons are identical, so they are coherent, monochromatic, and also one direction. Which of the following is not an essential component of a laser? Partially transparent mirror, it's a component. Fully reflective mirror, one of them is partially reflected or partially transparent. The other one is fully reflective mirror, correct? Active medium, of course, you should energize the atoms. That's why this is a part of, but convergence is not a part of lasers. Question number 9. Why is laser light useful for purposes of making astronomical measurements and surveying? Because lasers can be used to measure large distances, and they were also measuring with very high sensitivity. They are very sensitive. Errors in the calculation measurements are very low. Too low in the lasers. Question number 10. A diffraction grating used in a spectrometer causes third order maximum, yani m is equal to 3, of the blue light on the wavelength is given lambda to form at an angle of 6.33 from the central maximum, m is equal to 0. What is the ruling of the grating in its lines per centimeter? We will calculate d. D is the question. After that, from D, we will get what is the number of lines in centimeters. So m lambda over sine theta is the equation for calculating D. M is third order. Lambda is 904 nanometer, of course, multiplied by 10 to the power -9 for convert meter. Angle is given 6.33. So you will find how many meters this slit spacing. Because question is asking lines per centimeter, I am going to convert this meter to centimeter by multiplying 100. This is slit spacing in centimeter. After that, because n is equal to 1 over d in centimeter, d in centimeter is 1.33 times 10 to the power -3. When we divide them, we will get the number of lines per centimeter. An extended response. A double-slit apparatus for demonstrating interference is constructed so that the slits are separated by 15 micrometer distance, slit spacing. Of course, we should convert micrometer to meter. 15 times 10 to the power -6 meter. First order bright fringe, yani m is equal to 1. For constructing appears at an angle of 2.25 from the zeroth of the central bright fringe. What is the wavelength of the light? For constructive interference, we know that the equation is d sine theta m lambda. Because it's asking wavelength, simplify by lambda, simplify by m. So lambda is going to be d sine theta over m. D is 15 micrometer, which is 15 times 10 to the power 6 meter. Angle is given as 2.25. M is equal to 1. So we got the wavelength first in meter. If choices are given in nanometer, you should multiply meter by 10 to the power of 9 to convert nanometer. Question number 12. At what angle would the third order bright fringe appears? Third order, m is equal to 3. So you will calculate at what angle theta, sine theta, d sine theta m lambda, divide by d, simplify d. So sine theta is m lambda over d, then inverse it. You will find it. M is equal to 3. Wavelength, just we calculate in part 1. We will insert in here the wavelength. And then slit spacing is also given the question. We are going to insert in here. We will get the angle for third bright fringe. At what angle would the third order dark fringe? For third order dark fringe, m is equal to 2. So we are going to write the equation for dark destructive interference, d sine theta m plus 0.1 over 0.5 lambda. And then, because theta is the question, divide by d, then inverse it. Instead of m, write 2. Lambda is just calculated in part A, write it in here. This slit spacing is known, put in here. You will find the angle as 5.63.